Welcome to myprojectbazaar.com. Our product title is Dynamic Modeling and Control of Utility Interactive Microgrid using Specialization controller. Let us see about abstract of our product. The proposed operational strategy is mainly focused on using an appropriate energy management and control strategies to improve the operation of an islanded microgrid formed by photovoltaic solar energy and SOFC, that is a fuel cell, batteries and loads. This control strategy is to achieve decentralized power management of a PV battery fuel cell hybrid unit in a troop controlled islanded microgrid. In contrast to the common approach of controlling the PV unit as a current source, in the proposed strategy the PV unit is controlled as a voltage source that follows a multi-segment adaptive power frequency characteristics curve. The proposed power frequency characteristics of the hybrid unit and of the whole microgrid adaptive autonomously to the microgrid operating conditions so that the hybrid unit may supply the maximum PV power, match the load and or change the battery while maintaining the power balance in the microgrid and respecting the battery state of charge limits. These features are achieved without relying on a central management system and communication. Most of the existing algorithm too. The control strategy is implementing using multi-loop controller which provides smooth and autonomous transition between the operating scenarios. In this process is enhanced using of fuzzy logic controller. Next we see about flow diagram of our product. This is our flow diagram. Generally, from a control point of view, photovoltaic generation units can be classified into standalone and grid connected configuration. Due to the intermittent nature of PV power, battery storage is employed as a critical element in PV standalone applications to maintain the power balance in the system and enable regulation of the load voltage. Islanded microgrids share the same issue with standalone system, since the battery storage is needed to maintain the generation load balance and to regulate the microgrid voltage and frequency. In both cases, the power management strategy should consider the state of charge limits and the power rating of the battery. However, unlike in standalone PV system, in microgrids the battery storage can be connected to the microgrid bus as a separate unit. This the three kind of sources. One is the PV panel, another one fuel cell and battery. Both sources generate the voltage. After that, that voltage is converted into DC to DC using of these converters. After that, that voltage will be fed into the DC bus. In the DC bus, the load is connected, the DC load. After that, one inverter is connected, that is a DC to AC conversion with LC filters for regulating the harmonics. After that, that output is fed into AC grid bus. In the AC grid bus is connected to AC grid, and also in the point of coupling area one load is connected in the parallel. So overall process is conversion is DC to AC. Finally the load is a AC load. Next we see about running process of our product. In this proposed implementation is done in MATLAB Simulink environment. First open the MATLAB window and create a new model file. After creating that, we are arranging the elements from the Simulink library browser as per the circuit diagram. After arranging that elements as per the circuit diagram, we assign the parameters values for inductor, capacitors and panel and solar cells values. Here we using 72 solar cells for generation 44 volt in using of 1000 irradiance, and also fuel cell is used another source, and also wind generation is another source, and finally the battery energy system is connected in those system. Then the overall process will be converted into DC to AC, and finally the load is connected to grid. So first we see about the waveform of PV and IV curve, and before that we click the run icon, the simulation starts to run. So first one is the IV curve. This is plotted from current and voltage in the PV panel, and next one is the PV curve. This is curve plotted between power and voltage, and this is the solar battery output. Then this is the wind output, first one VDC and next one is the omega t and real and reactive values, and this is the solar power, current and voltage waveform, and next one is the SOFC output voltage, and this is the battery output. This is SOC, state of charge, and this is current and this is the voltage, and next one is the output voltage is getting from the wind side, and next one is the output voltage is getting the output DC load side, and this is the output voltage of another DC load sides, and this is the input of the inverter side. So here we seeing the variations between during the timing, and next one is the output waveform of inverter side, and the next one is the switching pulses is generated using a space vector pulse width modulation technique, and this is the output voltage waveform of in the load side, and this is the grid side voltage waveform. Here we voltage and current waveform, this is measured in the voltage from grid and load side. So overall output process will be increased using of this control technique. Thank you for watching this video.